Okay, hello again, everyone. Let's get it started. We have, I think, most of the people here. Good morning and good afternoon to all of you. My name is Alemohammad. I'm the Chief Data Scientist and Executive Director with Radiant Earth Foundation. Radiant is the organizer of this Spot the Crop Data Challenge on Zindi that I assume most of you have been participating in. This webinar is organized to basically go over some of the more technical tutorials about how to access the data, how to build a baseline model, and also open up a good amount of time toward the end, about 25 minutes, 30 minutes for Q&A from your side. So if you have any questions about accessing the data, building model, or any other aspect of the competition, please stay on, and toward the end, we would be kind of go over your questions. Today, I'm going to go over a very brief overview of the competition for some of you who might be newer to the competition, and then pass it over to two of my colleagues who will go over two tutorial notebooks about accessing the data and also, again, building the baseline model, and then a third notebook that I will also go over about another baseline model, basically multiple ways of building your model. If you have any questions in between, feel free to put it in the chat. And we will get to those after end of each presentation. But then with the more general questions toward the end, there will be time for those as well. So with that, let me share my screen. Yeah, you should be able to see my slides. Luisa, let me know if things didn't work out. So this competition is sponsored by many organizations that I will also acknowledge at the end. And it has two tracks, but just an overall picture of why is Spot the Crop. I mean, this is a very common practice that remote sensing data is being used more basically regularly to do agricultural monitoring, particularly in a sense of mapping different fields, crop types, and in a more advanced applications, the yield and production of the agricultural field. Because collecting those data is expensive and very hard to do on the ground at a scale, and remote sensing data, particularly open satellite data like Sentinel-2 and Sentinel-1 that we are using here, are available globally and consistently. They can be a replacement for doing that kind of census and collection on the ground. And at the same time, these satellite data have very kind of specific information content, like different spectral bands, or in the case of Sentinel-1, different reflectances of radar that have signatures of vegetation in them. So it is basically powering and deriving those applications because of the information content. And that's why we are doing this. And this is a data collected in Western Cape, South Africa. And we are trying to see if we can build a model through this competition that can replace, to a good extent, the extensive effort that has gone to collecting this data as a census on the ground and supporting the Department of Agriculture there, basically. So the goal is you will use basically a series of temporal time series observation from satellite imagery, both from Sentinel-2 and Sentinel-1, and then predict the crop class in a specific field. The way the data is structured is that, let me show maybe this image first. You will have these multiple bands and at different times. So each pair here is a different time. And then you have one set of labels for each pixel through time. In this case, for example, this square or the hexagon or the circle are different fields, the field boundaries and the pixels within them. And they all have the same crop class. So what you are going to predict or infer is one crop type per field. And for that purpose, we have included a field ID object in the metadata that you can access. But how you use the time series is basically up to you. So this was the reminders I was going over here, that first of all, pixels within each field have the same crop type. So that's the key piece. You do not need to use all the temporal data. If you want to kind of skip some of them, if you want to interpolate between them, you want to pick specific frequencies of observations, it's up to you. We have provided all the data because that's what the maximum basically amount of information you can get from the satellite. But if you can build a model that uses less data and has a very good accuracy, why not? We don't need to make models more complex. a key point, basically two key points about types of information you can use. I mentioned this in the original webinar when we had the hackathon as well. The absolute date time of the measurement is not a predictor. So for example, if you have satellite imagery captured in, I don't know, April of 2017, April 2nd, 2017, that absolute time value, April 2nd, 2017, is not a predictor. But the relative time, for example, this is, I don't know, 2 months or 60 days from the beginning of the growing season, that can be a predictor. But make sure you don't use the absolute date time as a predictor. That's something to keep in mind. The same with the, again, location of a field within the image chip. So you have image chips 256 to 56, and some fields are, I mean, fields are distributed around the chip. So if a pixel of that field is like, I don't know, 10 pixels from the top corner down and then 20 pixels to the right, that absolute location, again, is not a predictor. Make sure you don't use those information, because we had seen this used in other competitions. This is just a reminder to make sure you don't use those absolute information as predictors, basically. Yeah, I mentioned this, and this is the overall map of where we have the train and test data. The green here is basically the training tiles, and the orange ones are the test data. So you can use all the training data, or you can just pick some of them. But in the test, you will do all the basically inference and provide the information in the submission. These are the 9 different crop classes that you have in the data. And you notice that actually one of them is a fallow land. So it's an agricultural field that doesn't have any crop, but during the season is basically followed. So it is kind of waiting for the next season to be planted. And I appreciate if everybody keeps their mic on mute so that when speakers are talking, we don't get background noise. Thank you very much. And then lastly, evaluation metric, which is a cross entropy basically metric. Some of you might have used this in other competitions as well. So when you have a multi-class classification problem, we usually use a cross entropy problem, which in this case, we are trying to see what is the most probable class in your prediction of a specific object, in this case, which agricultural field. And then you get the logarithm of that and multiply by the actual probability, which is 1 in the true data, and then average that over all the classes. And then at the end, average over all the samples in the test data. So we have around, as I mentioned here, 87,000 training sets, and then 35,000 in the test set, and the classes are 9. So, and this is calculated on the Zindi side, but if you want to implement it on your end with your own split of train test validation, you can use this equation basically. And last slide, as I mentioned, this has been supported and basically organized with the sponsorship from our convening sponsor, the GIZ Fair Forward program, which stands for Artificial Intelligence for All. We appreciate their support. The Western Cape Department of Agriculture has provided the data and the problem. So the problem you're working on is a really real world problem. And they have been the provider of the census data, which we use as reference labels here. And then we have a platinum sponsor, the Computer Vision for Global Challenges Initiative, which has been supporting the prizes of the competition, as well as a gold sponsor, Descartes Labs. So we appreciate all the support that has enabled this competition. With that, I'm going to pause here and see if there's any questions. And if not, then pass it to my colleague, Kevin. There's one question from Aninda. Does every field have the same number of pixels? No. So this is the case. The fields are basically natural field boundaries. So they are not the same size. And for that reason, they don't cover the same number of pixels. But we will show in the notebooks that you can basically group by the field ID when you read the data and then get all the pixels associated within one field. But they don't have the same number of pixels. That is a very good question. Kevin, do you want to get ready while I'm looking at the data and the questions?
Yeah, sure thing.
So there's another question that in the stack.json file, you're seeing the latitude, longitude of the fields. Can you use them as features? Again, no. So you can use the absolute location, absolute time as a predictor. I mean, the fact that, for example, a field is located in, let's say, latitude 50, longitude 30, that is not a predictor of the crop class. The predictors are what you see through the satellite image, which is the like different bands from Sentinel-2 or the spectral, the reflectances from the Sentinel-1. So you should not use any absolute terms of location or time as a feature or predictor in your model. Yeah, thank you, Akash, for that question. Okay, in the interest of time, we will move, but if there's any other questions, feel free to post there and we can go to them. So the next speaker is my colleague, Kevin Booth, who is a Geospatial software engineer at Radian. Kevin?
Yeah, thanks. So yeah, we put together a couple of notebooks, and the notebook I'll be going through for you is this one, which will let you go through and download the test and train data, and as well as the labels, and then also split up the Sentinel-2 imagery so you can download individual bands instead of having to download the entire data set. So just for reference, each individual band of Sentinel-2 imagery comes to around 5 gigabytes. So you'll need at least the 5 gigabytes for the download, and then another 5 gigabytes on top of that to extract it. So if you're going to download just one band, you'll need at least 10 gigabytes free space on your computer. If you're going to download multiple, because we delete the archives after extracting, you'll just need the n number of bands times 5 plus 5, that amount of gigabytes. So this notebook, I'll just go through briefly. So this first cell here, we import all the required libraries that are needed for the rest of at least this notebook. The two libraries that aren't standard installed on your computer are pandas, which you probably will have already installed. And the second one is our Radian ML Hub Python client. We're just using this Python client to basically handle the downloads and retry if the downloads fail, and also basically restart the download from the middle of a download if it failed in the middle. And so normally, if you're downloading our data sets from our website, you would require an API key, but here we don't. But this is important to add here just so that the ML Hub Python client doesn't fail, that it doesn't see an API key. We just set this value here to not applicable. So this next cell here, we have a couple of different options. So you can set this first line here to true if you want to download the Sentinel-1 imagery, if you're doing the Excel track of the competition. If you're not, just set this to false and it won't download it. And second here, we can select which Sentinel-2 bands we want to download. So here I have it selected just to do the cloud mask, just to kind of speed things through this notebook. That's one of the smallest file or band files. It's around I think 30 megs. So yeah, just select which bands you want to download here, change it to true, and I'll go through and download those in the rest of the notebook. So this next cell here is a lot of code that just goes through and handles the download. So we go through, let me go down to the bottom. So the top part are just a bunch of functions, but here we select, okay, we want a train data frame and we also want a test data frame. And here I just have it set. This is, don't change these values. These are specific to the way our archives are structured. But basically it goes through, and you can see here we have a bunch of if statements that if download Sentinel-1 is set to true, it'll go and download the Sentinel-1 archive. And then for the Sentinel-2, it'll go through and only download the bands that are set to true. And so at this point, we also actually download the test and train splits, as well as the label files. The label files are always going to be downloaded. So once all the files are downloaded and extracted, you can see here on the side, So I have the test labels, the test Sentinel-2 cloud mask, train labels, and train Sentinel-2 cloud mask. So they each get extracted into their own individual folders. At that point, what we do is we go through and navigate through the labels stack JSON. So the stack JSON basically links together all of the label files as well as all the imagery files that are associated with each image chip. And what we do is we go through and load it into a data frame, and it will only load into the data frame the assets that are actually downloaded on your computer. So we can see here, once we have this all running and downloaded, we can look at the test data frame. We're going to filter off of the assets here. We just want to get the field IDs asset. And we can see here for tile 0590, it doesn't have a date time because the field IDs don't have a date time, and also doesn't have a satellite platform because the field IDs don't have a satellite platform. We can see which asset type it is, and then we can also see the actual file path. It's cut off here, but this will give you the direct file path to that field IDs for that tile ID. And next, here we can filter off of the satellite platform. So here we're going to select any assets that are related to the Sentinel-2 satellite platform. And here we can see for field 0590, we have at, I guess, April 1st, 2017, we have the cloud mask asset, and this will be the direct file path to that cloud mask for tile ID 0590 at this date time. And then lastly, in this notebook, we go through and we filter off of, in this data frame, any assets that fall within a specific time frame. So here I filtered off basically just in the month of April. We can see here all of these date times are in the April month. And again, if you have multiple bands downloaded, you'll see all the bands here. So you would see like band 01, band 02, band 03 for every tile within that date time filter that we've set. And that's basically this notebook. If we have any questions, I can take those now. But yeah, so we tried to split up the Sentinel-2 imagery to make it a little less of a heavy download. If we put everything into one archive at the beginning of, or as we had at the beginning of the competition, it was going to be around 60 gigabytes. So you would need 60 gigabytes plus another 60 gigabytes to extract it. So that was going to be around 120 gigabytes free space that you needed. But we recognize that most people won't need every single band to build their model. Some bands are more useful than others. And so we split it up into one archive file per band. Let's see. If we have loaded the data previously, will anything change with the new format? So this notebook is essentially giving you the same output as you had before. So in the previous notebook that we had, this would load everything into a train data frame and test data frame. And you would just have every single asset loaded into those data frames. So it's going to give you the same output. You'll see in the next notebooks that basically all we did was replace this top part of the code with the other top part. So yeah, there's not really anything that changes besides you wouldn't have all the bands in this data frame. Okay, and then another one, is it possible to download only some of the fields for rapid experiment? No. So I think there might be some confusion on the tile IDs and field IDs. So the tile ID is the 256 by 256 pixel chip. And within that chip, you can have multiple fields, or there could just be a single field within it. A couple of the fields are, just a handful of pixels. Other ones are much larger. But essentially, these archives that we're downloading, they're downloading every single chip in that train or test split. Any more questions? Okay, so do we need Zindi.Africa to register for the competition? Yes, to at least submit your actual submissions, you will need an account. But to go through and run through these notebooks are on our GitHub. It's Radiant Earth /MLHub-tutorials. That's where all of these notebooks live. But you won't need an account to actually download any of these data sets or train a model. Hamad, do you want to handle the coordinates one?
Yes, thank you, Kevin. So there's a question about we cannot use for example, coordinates, and this doesn't make sense because if we want the model, for example, we want to model fields that are closed, we can infer that from the imagery, but it is not. But it is much easier to use the GPS coordinates, for example. I mean, think about it. This is actually very much reasonable, and the reason is, let's say you are on the ground, you're going, put aside the imagery, put aside the machine learning model. Let's think about a logical way of doing crop type classification. You're on the ground, you see a neighbor's field and they're growing wheat. Then you go to the next field and they're growing, I don't know, barley. There is no geographical information that would predict the next neighbor's crop field versus this one, right? One of them is wheat because the farmer chose to grow wheat. The next one is barley. The next one is potentially something else, alpha, and the next one might be wheat. The absolute location or coordinate of those fields doesn't indicate what crop types should be grown there, or it is growing there. So now transfer that to the imagery world. So you have the imagery of that region. You're looking from the top, either aerial imagery or in this case, satellite imagery. The fact that one pixel is located in a specific latitude, longitude, that doesn't tell you, and it should not tell the model that, hey, this is wheat or this is something else. It is the spectral information in the imagery that would indicate what is that crop field. Even the thing that is growing in the neighboring pixel, that it doesn't tell you anything. I mean, if you use deep learning, the deep learning will basically, the convolutional layers will learn the patterns, but it is not about the absolute location of those. It is basically the shape of those, the spectral bands, the temporal phenology of the crop that will tell you what is growing in that region. So that is the reason, and it makes sense not to use any absolute location, because let's say you build a model, let's use this scenario, you build a model, you're using the absolute coordinates in Western Cape, I don't know, somewhere in the northern part of the state, then you move your model to the eastern part, and you're applying the same model. The coordinates doesn't mean anything there. The model cannot infer, oh, now that I'm in a different latitude, longitude, so the crop type should be something else. So for that reason, you should not use any absolute coordinate value or any absolute time value in your model. Yeah. One more clarification. Is it possible to download only some of the tiles? All tiles for a band gets downloaded. Is that right? Yes, I just said that. Yeah. So when you download in this new notebook, you get one archive folder, zip folder per band of the data, which contains all the tiles. Yes. And we will go in one of the notebooks later on to show you why you don't need all the bands, basically. There's a question about, okay, that could be close to a water source, plus water intensive crops grow there. Again, if it is close to a water source, you are not seeing that through the imagery. So you should not tell the model there's an absolute coordinate system there, because the model should infer from the imagery, from the spectral bands, what is growing there. The fact that it is close to a water source doesn't mean, oh, if it is further from the water source, those crops are not grown there. So you should not actually mislead the model about those things. Yeah, there might be some of those features, but if you want to do that, you should bring in a layer of water source information there, not the coordinate system. Let's say you don't know, I don't know, you have a map of reservoirs, or you have a map of groundwater levels, for example. You would bring that into the model, not again the absolute location of the field on the ground. Yeah. Cool. Edgar, can you get ready and share your screen? So the next presentation will be by Edgar Ssensalo. He's an AI engineer at the Sodzo Foundation. He is also one of the data Sherpas with the competition, who has been helping you guys on the basically questions about the competition or any other discussions. He will go over one of the notebooks, which is for using particularly Sentinel-1 data and building a model. Edgar?
Yes, let me share my screen just a minute.
Okay.
Can you see my screen?
Yes, we can.
Yeah, okay. So I'll be taking you through the baseline model that was created by Hamid. Some of the issues that most people were having, most of the participants were having, was with the use of the API, and this has been clarified by Kevin, as well as the issue about the data, which has also been worked on. So I'm just going to have a quick run through in this notebook. So as you can see here, the first cell mostly just is doing like importing the necessary packages that we'll be using, most of which Kevin had also gone through. So I'll just skip this and go right to, yeah, maybe I'll just add something to what Kevin said on the downloading the data. So like he said, when you're downloading the data, you can either download if you, let's say you have a poor connection, if your connection maybe fails or anything, it's able to resume the downloads, as well as you'd be able to, once you've downloaded maybe like the first part and you're trying to get connection again, it will download from it will like skip the already existing archive and then move to the next. For example, as you can see, if let's say, let me just try to expand this a little bit. Let's say if I had downloaded maybe the train set, and then for Sentinel-1, and then I lost connection, I would still be able to get the archive for the test set and just unzip that, as well as it deletes these archives after you're done. Okay, so also I'll just add that the load data frame one is primarily helps to move this data into data frames so that you can be able to easily work with it while giving you the necessary properties that are needed for the computation. This is an example of the train data frame. As you can see, what Kevin was trying to show earlier, for the assets like the HV and VV, you can see they do have the date and time for Sentinel-1. Then I will move on to the next cell. Yeah, so this cell mostly just shows the different asset types that we're working with in this data frame, such as the documentation, the field IDs, the field information training, the labels, the raster values. The raster values, they basically show how the crop names map with the classes, and then the VV, HV, in this case for Sentinel-1. Then I will just also give a hint onto this again. The observations here, for simplicity of this model, Hamid put 5, but you can either increase or reduce this depending on how much data you want to work with. You can change the number of observations. So in this case, we'll be looking at, it says 5 here, but we'll be looking at 4 at the fourth, let's say like the fourth observation within the time series. The fourth observation is what we'll be picking, just for the sake of this guide. Then here, basically, this is I call it like how we are processing the data. So we pick each tile ID in like all the tiles, and then we try to get a data frame from this, and using this data frame, and then we will be able to pick out the assets such as the labels. So we pick out the label assets, then get its path, and we use Rostario to read to open this this path, and we will store that into the label source. Then we will create an array out of all these labels, and we'll append this to we'll flatten that array first, then append it to the Y value here. Y value represents the labels in the model in this case. Then we'll have the fields, or the field IDs as well here. We are repeating the same process here. We access the field IDs using the file paths, and then we'll also use Rostario to open them, and then we shall store them in the field ID source. Then we create an array, and again we flatten it, and we append it to the field IDs value, in this case in the model. And then we also have, since this is a time series, we also have the date and times for the Sentinel-1 satellite platform. In this case, we'll also store these in the date and time tiles. Then here, what we'll be doing is we get a specific date, and we skip. We take like the fourth observation, and we'll try to pick the VV and the HV asset values in this case. So for a specific observation, the fourth observation in this case, in the time series, we will pick the VV and the HV, and after we're done with that, we flatten them as well, and then we put them inside an array. Then once we're done with that, we'll append these tiles. We'll create we add this into the initial X that we had here. And when we're done with that, we'll here, as you can see, we create a data frame. So basically, I think I had Hamid explained this earlier in this webinar, where he said that we have to group this data. So once this data has been grouped, we because the pixels that are in the same field will have the same labels. So what we do is we just group these together, and then it's much easier for you to determine where that pixel belongs, because if you have the groupings, then it's much easier for you to estimate where they belong. Then here we build the model while grouping by the field IDs, and then we get the mean. And as you can see here, we have the field IDs and the different values Here we're going from 0 all through to 7 and the labels as well. Then here is where we generate we use this to generate the training set and the test set using a random. We just create like a random size of the train set and the test set, giving the train set 70%, or in this case 0.7. And then for the fields, and then now we just assign these to the train fields and then the test fields. Then when we're done with that, here we will Hamid added some hyperparameter tuning just for optimization. As you can see here, this value can also be adjusted accordingly while you're doing the training. Then here we fit the model using random forest. I'm specifying the number of trees as we had stated here. And then once we're done with training the model, then we can come and carry out the we can carry out the predictions on the test data in this case. And I'll just go right to the end here where we generate the data frame that can be submitted. Yeah, so here you'd be able to generate the file, the CSV file that you can submit on the Zindi platform.
Edgar?
Yes, Ahmed.
So let's pause here and see if there's any question for you. A question from Akash. One small doubt, does field ID being 0 mean something? It comes in the data frequently with different label aggregation values in the test data. If you said this is not this line is your advice. So field ID being 0, it means there is no label for that pixel. So as if you have visualized some of the data, there are pixels in the image that don't have any label. They might be, and actually majority of them are the case, that they are not cropland. They are either bare ground, there might be water, there might be like built up areas, so they don't have any crop label. And there are very small percentage of pixels that are actually cropland but don't have any labels, and you're not dealing with them because they are very kind of rare crop classes that would be hard to classify them. So everything is excluded from the data. So in practice, any pixel that has a field ID of 0, you can ignore them both in the training and in the test. You are not asked to do any inference over those, and you're not training the model over those. That's why we are excluding those pixels from the test data as well. The basically line of code that you have in there, Akash. Is there any other question? Dabuya, you have a question? You want to type or you want to speak up? Yeah, you have written QN. I assume you have a question, so feel free to unmute yourself if you want to ask that. He's typing the question, or she is. Okay, let me get while we are getting that question, I have a direct message from one of you about, again, the location question. Let me see if I can translate that in another way, another perspective. So you all have some kind of preference about, oh, if a field has a specific crop type, the neighboring field might have a similar one, or it might be in a class of crops, because regionally crop types have certain preferences. Farmers grow certain types of crops in one region versus the other. That's a valid point, and that is true. So when you have a basically, and in this case, for example, we are in the western part of the Western Cape, northwestern part. Regionally, those crops, for example, are different than crops, for example, in the eastern part of the state. And that's why we are actually focusing in one part, because if you go to the other part, we would probably add 5-10 more crop types, and that would be a much more massive problem that we didn't want to kind of mix here. But having said that, those are relative information. So the fact that, oh, this pixel is wheat, and the neighboring pixel is also wheat, it's the same field, then 10 pixels to the left or to the right has a more probability of being wheat. That is true. That is a relative information in the sense of neighboring pixels, not an absolute value of the latitude, longitude of that location. That is what I'm trying to convey, and make sure you guys don't use the absolute value of the location. Because if you're putting the absolute value of location, the model is just confused. Why is latitude 50, longitude 30 a predictor of a crop type class? We should not use that as a predictor. But if you're using the relative information, that is okay. And then that is the case, for example, if you're using a convolution layer, that is naturally coming in because you're looking at the neighborhood and you're filtering those. That naturally comes in. And you are training this model on a regional data set, which is in the Western Cape. So the model is getting trained on the distribution of crop types, phenologies, the type of basically climate and the weather there, which is impacting the phenology indirectly. And you see that in the spectral signatures. So you cannot actually easily transfer this model to another region. That is the fact. But again, the absolute location of a pixel is not an indicator of the crop type, and it should not be used. So that is the reason for that. I don't have any other way of conveying that reasoning, but we are telling you, you should not use that for this reason. And you're only allowed to use the spectral informations and any relative information in terms of the time series of the data. Edgar, there's a question I think someone has. They said, can you scroll up to where the cell basically after you download the files, but I don't see what is then the
files. Okay, let me.
But I don't see any follow-up question to that. It just says, can you scroll up?
After you download the files, guess it's this. Is it
Yeah,
this?
I think so. The user HP, if you have any questions, feel free to ask. You have just asked us to scroll up, so.
Okay.
So there's a question about, okay, maybe I'm late, but I'm wondering on the size of the test data that looks like 2,881, but the required size to submit is almost 3,000. Where is the rest? Oh, I think this might have been my thing, that when I was running the notebook, I stopped it earlier than it was like going through all the test data. So yeah, the actual numbers is there. So if you run the notebook, it will go through all the test data and you will see the actual size in there. That might be just that. So the printout from that cell might be just me stopping the running of the notebook earlier than it should have been. Yeah. The other question, not a JS specialist, could you kindly talk about the bands? Edgar, do you want to take that, or do you want me to go there?
Pardon?
There's a question about, can you kindly talk about the bands and what they mean? Do you want to take that, or I'm happy to do?
I think you should take that.
Okay, no worries.
Yeah.
So think about bands. I mean, you're all familiar with images that you take with your cell phone, with your camera, right? When you take an image, it's always 3 bands of information in there, which is the red band, the green band, and the blue band. And the combination of those 3 creates a true color image that you always see. And these are the type of information that we humans, we see with our eyes. We always see the kind of true color spectrum of the electromagnetic spectrum. In the satellite world and also other cameras on the Earth, you can also observe information in other frequencies, which we call them bands when you capture the data. Those can be near infrared bands, it can be shortwave infrared bands, it can be what in the Sentinel-2 definition is red edge, which is somewhere between the red frequencies and the near infrared frequencies. Those observations that are captured at those frequencies are stored in different files, and we call them bands. So in the case of Sentinel-2, for example, you get 12 or 13 bands if you get all the information. Here we are only providing 10 of them. And this is what bands mean, basically. A different frequency of observation, and you get a different spectral response, basically. And in the case of Sentinel-1, because it is a radar data and not a kind of multispectral data, you will get a reflectance value. It's like radars that it's used for weather. Sometimes you see patterns in the TV weather reports, or even in the airports to detect airplanes and things like that. You send the active signal, you get the reflectance from that, and that is what we will see from Sentinel-1 as well. Edgar, can you go to cell 88? Yairo has a question that what advice is there for
88?
some? Yeah, I don't know if we have 88. Go down.
I'm not sure. Let me just check and see, because I don't
Yeah.
have 88.
Yairo, can you clarify that? Maybe you have run the notebook on your end and you are getting the number 88. But basically the question is, what is the advice if the system crashes when running cell 88 due to lack of resources? So it depends where you are in the notebook, but basically, okay, after n observations equal 5. Okay, I know where that is. Scroll up then. It's where you're loading the data to X and Y. Yeah, right there.
Just a minute here.
Yeah, here, exactly. So here you're basically loading all the data into your memory because you're literally reading all the train data. Things you can do here, and this is a good question, is that, so, I mean, here we use only 5 observations in time, just for one purpose of reducing, again, the memory usage. You can reduce that number, or you can reduce the amount of data you use for training. So rather than loading all the data, for example, in this case, in the last loop, which we go over different time observations, we load the VV array, basically first the VV source, and then we flatten the VV array, and you basically append all of that to your X vector. You can pre-select that. You can say, okay, randomly select some of those pixels, not all of them. In that sense, you're reducing the number of data you feed into your model for training. You don't need to, but you will go over all the tiles, so you have a representation geographically, but in each tile, you just select some of the fields, not all of them. So you can skip those. There's one more question. Is the entire test data on Sentinel-1 or both? So the train and test data are just geographically different from each other. So there are different tiles in the region. In terms of the input data, Sentinel-1 and Sentinel-2, depending on the track that you are, they have both of them. So if you are in basically the regular track, you will have only Sentinel-2 as input, both for training and test. If you are in the XL track, you will have both Sentinel-1 and Sentinel-2 as input, and as input for both test and train. So it doesn't, the Sentinel-1, Sentinel-2 doesn't change from test to train. It changes from track regular to track XL. Any other questions? We have one more notebook to go through, which is relatively similar to this one, but it's more about Sentinel-2 that I will go through. But I'll pause here if you have any other questions from the notebook Edgar presented. Nothing. Can you explain the sampling part? Not sure which part they're referring to. Edgar, do you have any?
What does he mean exactly by that?
That you just explained. Oh, the one, Anita, can you clarify? You mean the one that we just talked about, not loading all the fields? Okay, okay. So, I mean, this was just a proposal. It doesn't mean you should definitely do that. So what you're doing here, where you see the screen now that Edgar has up, after you go over different tile IDs, you load all the labels into the Y array, then you get all the field IDs into the field IDs array. Then you go over different time observations, in this case, only 5 of them, and you load the basically features or the input data, which in this case is the VV and VH. And at the end of that loop, we basically append that to the X of tile. So we use all the pixels in that tile and use them as training, and then later on as test. I mean, for test, you should do because you're doing the inference and submitting. But in the training, you can add a basically randomized number here and say, okay, if I have, I don't know, 256 by 256 pixels in this tile, I don't want to use all of them. I mean, some of them don't have labels, so you're already excluding them later on. But those that have label, I'm just going to select 50% of them and feed it into the model. So basically, you're doing a sampling of the training data and not feeding all of that to the model. That's basically the sampling part. How you do that, it's basically your innovative way of doing that. But that's just a proposal to reduce the number of data points you're feeding to the model to save some memory. Yeah. HB has a question. It takes time to run the cell where 5 observations was used. So exactly where Edgar is sharing now. Is there a way we can do that in a simpler form? I mean, Edgar, do you have any suggestion? I mean, we can give you all the solutions, but it's your innovation. But yeah, Edgar, you can go ahead.
Yeah, I think maybe the easiest suggestion I'd give would be to maybe like increase the number of observations so that you pick only you get like fewer observations from the fields, instead of taking in a given timestamp, instead of taking so many. Maybe in this case we're looking at a gap of 5. Maybe you want to take something that is maybe higher, so that you have less observations picked up, and then they would easily be able to do the processing much faster. Because I had the same issue with mine, because the resource is not quite good on my machine as well. But if you can maybe use fewer observations, it would make it quite faster. You'll be able to complete this processing quite faster, because for machines that are not very strong in the compute, they always fail to run. They've been failing to run, at least. Also, just to add this, I hope that no one is using Windows, because Windows kind of like fails to download the archive. I don't know what weird thing it has, but it fails to download the archive. So when you're trying to download, it kind of like has maybe we were talking about this with Kevin. I think it has like a limit in how many files it can download from the archive. So it fails to complete all the downloads. So I think it would be best to use like Linux or Mac in this case.
Thanks, Edgar.
I don't know if that helps him in any way.
Yeah, if there's any other question, feel free to add in the chat. There's one more about the tile size. They say 256, 256, the tile size. Is that supposed to be a constant? I'm not sure what you mean exactly by that, but yeah, the tile sizes are exactly the same. So all the tiles are 256 by 256. That's how we have split the data. If that clarifies the question, or if you have any further question, let us know. Yeah, but yeah, the tile sizes are constant. They're all 256 to 56 in this case. So if there is no further question, maybe I can go over the next notebook, which is very similar, but it's for Sentinel-2. Thank you, Edgar.
Thank you.
Okay, 1 second until I bring this up. Share screen. Give me 1 second. So this is the other notebook that we added to the repository actually the other day, I think yesterday. This is the same crop type classification model, but for Sentinel-2. And you can use this similarly to the notebook that Edgar just went over to build a model using random forest, but using only Sentinel-2 data. And difference here is that in Sentinel-2, as we mentioned, and Kevin went over the data preparation, you have multiple bands, but we are going to show you how you can use fewer bands. And also because this is a spectral information, you have pixels that are cloudy. So we are going to show you how to exclude the cloudy pixels from the data and basically not use them in training your model. Because when a pixel is cloudy, it will basically cause noise and build trouble in your model. This is not a situation with Sentinel-1 because radar data is transparent to the cloud. And you don't have a band for cloud in the Sentinel-1, you just have the VB and VH. But in the Sentinel-2, you have all the spectral information, the bands as you see 01, 02 until 12 or so. And then you have a cloud layer. So we're going to show you how to do that. The initial part of the notebook is very similar to what Kevin and Edgar went through. So I'm going to skip those. This is the packages you load. And then here, it's just the bands that I have changed. So we are not downloading Sentinel-1. We are only dealing with Sentinel-2 bands here. In this case, I'm loading band 3, 4, band 8, and the cloud layer. So why we are doing that is that band 3 and 4 are the green and red bands in the Sentinel-2, and band 8 is the near infrared band. These are the bands that are most sensitive to the vegetation. So this comes from, oh, what is the knowledge of remote sensing? You can go and download all of these and fit it to the model. We have provided that because there is definitely more information there. But the key bands, the ones that if you want to minimize your resources and build the basic model, would be to use the green, red, and NIR and use those as basically features in your model. And then the CLM is basically the cloud probability mask that will give you an indication of how cloudy each pixel is. This is a classification layer that comes from Sentinel-2. So we are downloading that one as well to basically filter the cloudy pixels later on. Again, this part of the notebook is very similar, downloading the data and loading to the data frames that I've just changed them to competition train, competition test, just for simplicity. And it's basically the very same code, and you just select the bands, and then the data frame you will get at the end has all these different bands, band 3, band 4, band 8, the CLM band, and again, all the different types of assets as you have seen in the past, the documentation, field IDs, labels, raster values, and everything. So this is, if you get a unique method on the assets, you will see these. So we will start with the train data. So we create the trained IDs, tile IDs for the training set, basically. So we get those. Here, again, a similar approach to what Edgar went through. So for simplicity, we're just using 5 images through the growing sys, and then picking 5 there's no like mathematical reason for that. It's just a simple number for building your baseline model. It's up to you how you want to deal with the time series data. And I think that's the key part of the competition, to see how you can optimize to build a model that can use all this spectral information the best way. You can assume to use the first 5 observations. You can say, oh, I want to use like the other notebook, every 4th observation, but totally 5 of them. But ideally, I would say it's best to use observations throughout the growing season. That's the key piece to keep in mind. But here for simplicity, we just use 5 of them. Similarities and differences in this part of the notebook. So you're still using random forest. So we are going to create an X variable and a Y variable. The X being basically rows and columns, which are the basically features and the pixels and features in rows and columns. And then the Y being the labels. And the field IDs, again, it's the field ID number that we will use the feature group by later on. Similarly, we get this specific tile, the pixels for that tile. We load the labels. These are very similar code to that part. We get the field IDs of that tile. We get all the basically date times, and you note that we are using now Sentinel-2 here. This is the difference from the previous notebook. And then we are just loading 5 observations, the first 5 that are cloud-free, basically. How we are doing that is that for each date time, we first load the cloud mask. So the cloud mask is a similar structure data. It is a raster. So we use the same function, the raster.io, and open that. We pass the date time. We get the basically a row in the data frame that is the CLM, and then we get its file path. And then we read that data as a raster layer. So CLM max is basically the maximum cloudy pixel in that raster. So this is the actual raster when we read them. And then we call the numpy max function on that to get the, okay, what is the most cloudy pixel in that 256 by 256 tile? This is just a simple way of doing that filtering. You can go and do this pixel by pixel and get all the pixels that are not cloudy and just ignore the ones that are cloudy, or you can decide at the tile level. Again, this is where your innovation and your creativity will come into building better models. Here for simplicity, we just get the maximum of that. And if that CLM max is less than 25, we start reading that data. So where did 25 come from? I have a comment here. So these are 8-bit images. So if you load one of these cloud masks, you see it has values between 0 and 255. That's a typical 8-bit data set. And 255 means that, okay, this is fully clouded. That pixel is 100% probability cloud. Here we are using a threshold of 10%, meaning that, oh, if the probability of a pixel being cloudy is less than 10%, we want to read that pixel. We are okay with a little bit of noise. If it is less than 10%, that is okay. And 10% of 255 is 25.5. So that's why we are looking at 25 here. So anything less than a 25 number would be translated to 10% probability of cloud. If that is the case, then we start reading different bands. So in this case, this is very similar to the, again, previous notebook, but we have now 3 bands. We have the band 3, we have the band 4, and band 8, basically the green, the red, and the near infrared. So rather than VV and VH, we have these 3 bands here. And we are not using the cloud as a predictor. Cloud was just a filter layer to make sure the data is clean. And we read the cloud-free data. After we read these, we similarly flatten them. We append them to the X of tile. We just have a breakpoint here. If we reach the 5 observations, we stop. And then we append those to the global X, which is our feature array, basically. So that is the main part that is different from the other notebook. The rest you will see is actually similar. I will show you now. But I want to reiterate that the main piece in the Sentinel-2 world is, oh, first of all, you don't need all the bands. You can go with fewer bands. And in this case, red, green, and NIR are the ones that are the most predictive for crop and vegetation, broadly speaking. If you're doing like forest mapping, you will use the same. If you're going to go and add more, you can then start adding more bands to that, like the red edge bands, the sewer bands, and others. But you can start with these 3 bands. And then the cloud probability is the other kind of differentiator from Sentinel-1, that you don't want to read pixels that are cloudy. Another way of doing this is you read all the data. You mean different time observations. And you read the cloud pixel as well, the cloud probability, and then you just drop the pixel, the observations that are cloudy, and you interpolate between those 2 other observations that are before and after the cloudy pixel. You can use interpolation as well. So that is up to you to decide how you want to treat and deal with the basically cloud masks. So the rest is similar. We get the X to a data frame. We add the labels and field IDs. Then we remove those pixels that don't have a label or corresponding field ID. Basically, as the question was, these are pixels that are not cropland and they are not as part of the competition. You don't need to train the model on them, and you're not asked to do any inference in those in the test data. For building the model, we do a similar thing here, that we aggregate all of these fields of the pixels based on their field IDs. We get their mean and we get the data group. So this is another place you can do your own creativity and innovation. You want to take the mean, you want to do another method here for aggregating. You can do that. You can also think about, maybe I want to do a pixel-wise classification and do the aggregation after I do the inference. So in this case, we are saying, oh, all these pixels that are associated with a field, we are going to group them, take the mean of the observations or the features, and then feed them into a model to predict the crop class. Another approach is, oh, I want to do the prediction or both the training and prediction pixel-wise, and then do the aggregation afterwards. That is up to you to decide. Again, this is just one way of doing that as a baseline model. Next, we will basically create our own train and test in the training part of. That's why we had the competition train and test data frame at the top, so it doesn't get confused with this train and test. We split the data to train and test. This is very similar to the code we had in the Sentinel-1 notebook. We use the this is a random number choice from the NumPy package, and based on the field IDs, we randomize those to test and train. And then similarly, we use a random forest with 50 trees, 3 jobs, just because the number of CPUs I have here, and then we train and feed the model. Very similar here again. And then we go over the competition test data. We load that data frame. We are taking a very similar approach here. We use the field IDs. We then read the date times. We similarly filter by the cloud mask. We don't want to, when we didn't train a model on data that is cloudy, we are not going to use those for test either. So here we are just using pixels that have low probability of being cloud, in this case, again, less than 10%. And then loading the 3 features, stacking them up, appending them to X style, and then creating the X competition test. Similarly, dropping the ones that don't have a field ID, meaning they are not part of the test or inference part. So we are not going to do any inference on those, and then grouping them by. So here, whatever method you use at the top, you're going to use here as well. If you go by mean, median, or any other kind of aggregation method, you're going to do the same here and get this basically data frame of all the field IDs and different observations throughout the time that you have, which you have stacked together. And then you're going to do a probabilistic prediction. So the random forest predict probability is going to give you a probabilistic prediction for each object or each input in your data, in this case, each field. And then the probabilities are going to be, what is the probability of that object, that input, being a certain class. So here we have 9 crop classes. So the output of this is going to be 9 probabilities per row of your data. And that is how you want to submit the basically predictions to Zindi as well. We want to see in a probabilistic sense, how good is your model? And that's how the cross entropy function that I showed at the beginning comes in, because you're looking at the probabilities here, not necessarily deterministic classifications. How you interpret those in a real world problem, it's again another thing. But here, for simplicity, we are asking you to submit the probabilities, not thresholding them, and just give us the basically the most probable class. And that's how you will basically structure your data after you get the probabilities. You put them in the data frame, add the basically crop IDs as column names, and the field IDs associated with those for each row, and then basically write those to a CSV file for submission. As you notice, the like last 70% of the notebook was very similar to the Sentinel-1. The main difference is how you do feature selection in the Sentinel-2 world. And in this case, we are using the cloud probability and also number of observations in time. So before stopping, I want to add one more thing. So in the XL competition, you're asked to use both Sentinel-1 and Sentinel-2. The notebooks that we have shown you today is one of them for Sentinel-1, one of them for Sentinel-2. Your innovative and creative solution is how you can combine those two to build the best model for the XL track. The XL track, you're basically dealing with the same amount of labels, but you have much more number of features and observations as input data. So how you want to treat that is up to you, whether you want to combine all of that in one model, feed it to the basically model, have all the features from Sentinel-1 and Sentinel-2 in one batch. You want to do a stepwise classification, do one with Sentinel-2, one with Sentinel-1, and then combine them in a third model. It's really up to you to decide how you want to treat those observations and input features. Yeah, so with that, I'm gonna stop and then see if we have any questions, and we have about 15 minutes left. So if there's any other question related to this notebook tutorial or generally about the competition, feel free to put them in the chat. So please, I did not get the answer to my question. I think HP is off. I'm not sure what was the question. We mentioned that. So let me go over others and then we can get back there. You have to submit your final work notebook in addition to the submission CSV file. So if you are one of the winners of the competition, based on the rules we have with Zindi, yes, you're asked to submit your notebook, basically the whole pipeline of how did you start from the data to get your inference and submission. And that should be fully reproducible with documentation, because we are going to publish those as open source models that you're going to be the winner and the owner, but it's going to be shared with the community. So yes, if you are the winner, you are asked to submit your submission, your code. Has a question that there are 8 labels. The label 0 is excluded from submission. If we submit label 0, we get an error. Yes, label 0 is basically no data. You should not predict any class as 0. As we mentioned here in where we are doing the processing, anything that has a label of 0, we are going to exclude that, because those are pixels that don't have a label. They are not a cropland class. So they should not be included in your training and not in the inference part. So that's why you should not have any 0 in your submission either. If a field have very few pixels, is it possible to use computer vision? I assume by computer vision, you mean like deep learning neural network models. You can still use them. We had another competition about a year and a half ago that if the field sizes were even smaller than what you have here, here we have field sizes that are, I don't know, 20, 25, 30 pixels at a time. In that case, we had some of them that were on the order of like 6, 7, or less than 10 usually. And one of the winning solutions was using a convolutional layer, and it was successful. So I'm not saying it doesn't work, but it may not need that complex of a model if the field sizes are very small. So start with the more simpler models, and if you can improve them with the simpler versions, then try to get to more complex deep learning or convolutional layers. Yes, but you can use them. Yes, there is no problem with that. Stop sharing. If there's any other question, feel free to put it in the chat. Or if you want to ask, feel free to raise your hand and you can unmute and ask the question. A question about the hackathon. So there was an issue about the arrangement of crop IDs on submission during the hackathon, the early days of the competition. The one on the provided notebook gave worse results, but on some rearrangement from some organizations, the scores improved. Any word on this? I'm not sure what was the issue. If you can elaborate on that, or if you can give me more details, I'm happy to check on that and let you know. But honestly, I don't have the details on that. I don't remember what was the problem. Maybe I should check with Zindi and get back to you. But if you can elaborate on that, because I'm not sure if I understand what was the problem exactly. And feel free to unmute yourself if you want to explain that in more detail. Okay, so there are two. I'm reading the post that and in the shared here. So there are two problems there. I think one of them I know. Okay, now I know what you're talking about. So one of them was that the field IDs that were included in the sample submission were more than what it was in the test data. Yeah, we noticed that issue after the hackathon, and Zindi told us, and we updated that. So I think that was a different problem than the column. So that was corrected, and the data during the challenge when we started on July 4th or 5th, we corrected that. So that was a mistake on our end, because some of the fields were not included in the test data while we had them as labels in the kind of raw data. And we corrected that. So that is corrected. And I think it was accounted for in the challenge scoring. I can check with Zindi on that. On the second point about the order of the columns, I don't think that is the case. I will check with Zindi on this. This is new to me, honestly. I didn't know about this issue, but I doubt that is the case, that the crop, because when we say crop underscore ID underscore 1, that literally means label 1. If you're like using label 7 for crop ID 1, that doesn't make sense. Now, if you're getting a better score there, it's just by chance. The ID, the crop ID X, that X is literally the label you have in the data, whether it's 1, 2, or whatever that number is. So I will check with Zindi on this and get back to you about that. But to the extent I know, the order, if you're changing the order and getting better results, that's just by chance, because the actual classes are the IDs there. Thank you for bringing it up. I will definitely check on that, and we will post an update in the forum so all of you can follow. Any other questions? If not, yeah, thank you everyone for joining us today. Hope you enjoy using the data and competing in the competition. Just a quick update. This is not official. We are going to announce it on Monday, but we'll probably extend the competition deadline, because there was some hiccups about using the data, the size, and the large, basically, archive folders. And some of you had problem accessing that, and we updated that just recently. We are trying to extend that deadline. So, but we'll officially kind of confirm the date on Monday. So look for some updates and announcements on the competition page. Thank you for your patience with that. And thank you, everyone. And thank you, Edgar and Kevin, for helping with the tutorials today. Have a good one, everybody. Bye-bye.